I'm so excited. I love this topic. So, right. I think we've talked about this before, and actually I'm going to bring up the idea of solids, liquids, and gases. The fact that matter sticks together to become a solid because it has a lot of intermolecular bonds, okay? Liquids basically are liquids because some of those intermolecular bonds have been broken, and gases have no intermolecular bonds. Okay, so if you see me do something like just IM, I'm talking about intermolecular bonds. IM is my intermolecular bonds. So again, solids have a high degree of bonding. And I almost wonder if solids, which came first, the bonding or the motion? Like they don't move very much, right? Solids, they're just they just vibrate. Gases have no intermolecular bonds and have a lot of motion. Okay, liquids somewhere kind of in between. And here is this. Let's see, I brought all these up. Let's see how it is. One, do you remember the whole, I guess it was in thermodynamics, where we talked about it takes a certain amount of energy to like melt something, and takes a certain amount of energy to like take a liquid and make it go into a gas. Those were latent energies, and you can look those up on a table. Actually, we're going to be looking at those a little bit more. So it takes energy to break bonds, and when bonds are formed, energy is released. Okay, so like what I just described was adding energy, and if you go backwards, like if you go from a gas to a liquid, bonds are formed and energy is released. If you go from a liquid to a solid, bonds are formed and energy is released. So those are intermolecular bonds that we've talked about before. So now, actually, I printed this off for everybody, because this is something to have handy. So, here is. So listed at the top is the strongest type of intermolecular bond. And if you're like me, I would argue that that's an ionic chemical bond. Okay? So ion. One piece is an ion, the other piece is an ion. The thing between them is, I guess, a type of intermolecular bond. It's the strongest, okay, called an ion intermolecular bond. Okay. Then we move to an ion dipole. Now I have a slide here to say what a dipole is. Okay, but if you just above yours if you want to, or just remember it if you want to, either way, anytime you see the word dipole, think polar molecule. So all of that, molecule, singular. All of that you've been doing in the first part, identifying whether a molecule is polar or not, it creates what we call a dipole, and I'll just kind of show you. If this is my polar molecule, I'll try to make one end fat and one end skinny. Okay, this I'll make partially negative. Lion's share of electrons, I'll make this one partially positive. That's the dipole. Okay, so ion dipole. So it's possible that you have. I'll just go ahead and put an Na up here, as in sodium chloride, and a Cl minus over here, right? And it's not any big hairy deal. That dot, dot, dot. Okay, those are intermolecular bonds between some blob, that's a polar molecule, and something that's an ion. Okay? It's the second most powerful of the intermolecular bonds. Okay, we're going to see water's polar. Actually, water's a special type of polarity, but it would do ion dipole bond. Hydrogen bonding, okay? If you want to, and this will make more sense later, this is a special polarity, special polar, and we're going to see the conditions. They're not that hard, okay? Basically, somewhere on your molecule, you need to have an O bonded to an H, or an O bonded to an N. Oh, really? Are you serious? No. The second one, I got that wrong. Or nitrogen bonded to an H, sorry. And the last one is fluorine bonded to an H. final answer. Okay, so these are 3 different scenarios. If you have them on your molecule somewhere, okay, that can be the 3rd most powerful intermolecular bond. That's hydrogen bond. Okay, after that we have ordinary dipole-dipole. And so I said dipole, think polar. Okay, so basically you have just 2 polar blobs. Okay, so you have polar and polar. Polar meets polar. Okay, and just to kind of go ahead and let the cat out of the bag, if I went ahead and made my blobby thing, sorry, partially negative, partially positive, I made another blobby thing that was another molecule that was polar. I would line the partially positive one of my second molecule next to the partially negative one of my first molecule. And that thing in red there, that's the intermolecular bond. Okay, so that's ordinary dipole-dipole intermolecular bond. Then we have dipole-induced dipole. So dipole, you guys have written polar. Induced dipole, we'll write nonpolar. And we'll call it a day. Won't call it a day. But here you have something, you have a polar molecule and a nonpolar molecule. I'm going to kind of backtrack a little bit. I'm going to say even polar molecules can have induced dipoles. But if it's nonpolar, the only thing it can connect is an induced dipole. And then last but not least, we have induced dipole, induced dipole. So it's nonpolar and nonpolar. I'll just put NP-NP. Nonpolar dash nonpolar. That's it. So an asterisk down here, let's see, how do I say this? You have to have at least two things if you're going to get these combinations. So you must have a combination if you have things that are connecting that's in ion and polar, or ion and dipole. You must have at least 2 different things if you have something that's polar and nonpolar. Okay. Put another way, this slide just kind of revisits those different types of bonds, and it says pure substances will have, if it's pure, remember what pure means is it's only got one sort of compound, okay, or one sort of element, okay. So options for what's holding that matter together is ion-ion, hydrogen bonding, dipole-dipole, or induced dipole. Makes sense, because it's pure. Okay. So I told you earlier what dipole-dipole is. A dipole interaction is you must have a pair of molecules that are both polar. And it's kind of like I showed you a minute ago. The opposite charges are going to line up with each other. Dipole-dipole. 2 polar substances. Now it doesn't have to be pure though, because you can have 2 polar substances that are different and they're both polar, and they'll do that. Okay. So electron-rich red ones connect with the blue ones. They're not showing you the dot, 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 but that's kind of what's going on. Okay. This would be dipole-dipole. So make sure we're all on the same track. This one would be just ordinary dipole-dipole. Okay. So hydrogen bonding. So hydrogen bonding, like I said, your hydrogen is connected to, and it's almost 2 criteria, they say. It needs to be connected to an atom that is small and an atom that is highly electronegative. So that's why I was kind of looking at the periodic table just a little bit ago. If you find nitrogen, oxygen, and fluorine, of course, they're all in the same period. They're all just in that second period. And remember, electronegativity increases as you go up. So they're basically the smallest, most electronegative that you can have. Okay. So then you'll end up with this sort of deal. And so this is my, and in organic chemistry, they just kind of say R. That's something else over there. And this is my oxygen and my hydrogen. So what happens then is just within that, in this case, little hydroxyl group, you have a partially negative and partially positive. That's it. Okay, we could replace that with an with an NH. And again, you would have a partially positive over the, you would have a partially negative over the nitrogen and a partially positive over the hydrogen. And last but not least, we have a fluorine and a hydrogen. And we end up with the fluorine is partially negative and the hydrogen is partially positive. So those are kind of just your options for hydrogen bonding. And it's those sites then that do the heavy lifting to go ahead and create those strong intermolecular bonds. So a water molecule actually has, you know, two partially positive hydrogens and one partially negative oxygen. So it would arrange itself like this. Okay. Two water molecules. But that's not, so we're all on the same page. That is hydrogen bonding. Okay, so it's stronger than ordinary dipole-dipole. So picking on water, or I guess not picking on water, ammonia, NH3, we definitely meet the criteria of hydrogen bonding. Okay, so here's two ammonia molecules. HF, hydrogen bonding. You don't see a lot of, because I'm like, really, what other molecules do you have where you have a fluorine covalently bonded to a hydrogen? Not a lot. The HF molecule is all I can think of right now. Okay, so going back to water, picking on water. Water in its solid state, it has the highest degree of intermolecular bonds. And this is kind of showing you what water would look like. And I don't know if you can see kind of a hexagonal or six-sided figure there, but there's definitely, we have that going on within the solid water matrix. So if I compare solid to liquid, I guess there should just be fewer intermolecular bonds. So we're kind of showing some of those intermolecular bonds have been broken between the solid and the liquid. And these are just the same. The blue ones are, I think they're trying to show you back behind kind of the plane. Yeah. But they're just water molecules. Yep. There's water in its solid state. There's water in its liquid state. So the temperature at what something boils, we'll be talking more about the phenomenon of boiling. Boiling is so awesome. You probably got a sense for what boiling is already. Boiling is basically you've added enough heat to your liquid that some of those intermolecular bonds are going to break, and it's going to go from a liquid to being a gas. That's kind of at the crux of a little bit of what boiling is. So here's the deal. Does this make sense that the stronger the bonds when it's a liquid, okay, the higher you have to heat it before they can break, okay? So the temperature at which something boils is an indication of the degree of how much bonding we have going on in its liquid phase. So we're going to actually see a little video here with some compounds, some kind of analogous compounds. Of course, we're familiar with H2O, right? If you find, oxygen is above sulfur, selenium, tellurium, okay? So notice we could have H2O, H2S, H2SE, H2TE. Just basically substitute that oxygen out for something else. But I don't want to, I just preface this little video you're going to see by saying only when you have H2O do you have hydrogen bonding. H2TE, H2SE, H2S, no hydrogen bonding. So kind of told the whole story there. So this is kind of a similar thing. Let's see what we got here. Again, these are all boiling point temperatures here along the y-axis. Is that the y? That is, isn't it? Oh my gosh. This is the x, right? Okay. Yes. Okay, thank you. Down here along the x-axis, we have how big is the molecule in AMUs? How much does it weigh? So, you know, we kind of have analogous compounds. We have CH4, swap out instead of a carbon. Notice right under carbon is silicon. Right under silicon is germanium. That's why they did that. Basically, you're substituting out. Okay? So those are kind of analogous. And again, it's like the trend we saw a minute ago, aside from H2O, the other hydrogen compounds, that the larger they are, the higher the boiling point temperature, for sure. But now here, the cool thing about those that I circled is those are all H bonding. Okay, and so basically they're kind of outside of the trend for those analogous compounds. All right. So hydrogen bonding, strong, makes the boiling point temperatures high. So, we didn't really spend much time talking about ion-ion, but we didn't really talk about ion-dipole. I gave the example of, I think I tried to kind of give you an example. Hydrogen bonding, ordinary dipole, ordinary dipole. Induced dipole can happen in pure substances. Both molecules are nonpolar. Okay? Nonpolar. There are some synonyms, and there's one more synonym coming up for induced dipole. And how do I? The only thing, and not everybody's necessarily giving birth. Have you ever heard somebody ready to go have a baby, and they're so ready, and the baby's ready and everything, so they induce labor? And that's how I think of it, sorry, but induce labor. So in this case, basically, we are inducing a pole on something that doesn't have a pole, or a dipole on something that does not have a dipole. Induced dipole, induced dipole. I'm sorry, but that's all I think about it, okay? To me, that sums it up. Okay, induced dipole, induced dipole. So induced dipole is not reserved just for molecules that are nonpolar. Polar molecules, what we're going to see here in a minute, there's a chart coming up to show you that between polar molecules, you definitely have the dipole, but between polar molecules, you can also have this induced dipole effect going on. Okay. So, and this is getting a little bit along the lines, you know, the trend we saw, the highest boiling point temperature was the largest, okay? In a sense, we're going to see that large atom is easier to induce a dipole onto. And so that's why it kind of kicks butt with that. This says the total amount of dispersion forces, okay, increase with the molecule. The size of the molecule also increases with the size of the atom. So maybe this will help. I got a little video and a picture to kind of show you how could you take something that's nonpolar and make it have a dipole, which seems kind of strange. And that's just, it's almost like, it's just kind of the statistics, the unevenness of where the electrons are going to be, electron cloud's going to be. Because if we look at, we're picking on iodine. Iodine is one of the diatomic elements, so it actually goes around as I2, okay? So if we look at how I2 molecules stick together, it's actually got to be this induced dipole.
An iodine molecule has, on average...
Okay, basically you have something minding its own business. Its electrons, or electron cloud is even. Okay, it becomes disruptive or uneven, where the left one is partially negative side and the right side is partially positive. Okay, and then to me, the way I think of it right now is it can actually then kind of induce that on a fellow molecule once it's that way. But if you think about it, I2, that material, iodine, solid iodine, is, how could it be solid? How could those little I2s stick together? Because it's nonpolar. And the way it sticks together is this one, induced dipole, induced dipole. So here's I2, and this is Br2, bromine. And do they almost kind of, the haze is real. The haze means that actually it doesn't prefer, let's see, yeah. Bromine is bromine a liquid? I guess it is. So Br2 is a liquid, I2 is a solid. But do they look kind of unstable? Because they look like clearly they wouldn't mind being a vapor, as you kind of see the color in the Erlenmeyer flask. They're just easy, it's easy for them to slip their intermolecular bonds. Liquid down here, vapor up here, solid down here, vapor up here. I2 is one of those cool things where it sublimes. It skips the liquid stage at normal atmospheric earth pressures. So that's kind of cool. Okay, so I mean, the whole induced dipole is something to wrap your head around. And this polarizability goes along with inducing a dipole on something. If a dipole is induced, if you take something that's nonpolar and give it a partially negative, partially positive region, what you have done is to polarize that otherwise nonpolar molecular atom. Okay, so the polarizability of material says how likely or how easy is that to happen. And there are some trends with regard to polarizability. Remember, polarizability all goes back to that induced dipole sort of effect, polarizability. Polarizability increases with more electrons. And so I guess I would just go back to when we looked at, we compared H2O to H2S to H2SE to H2TE. So tellurium had the most electrons, it was more polarizable. Okay, so it actually could have these dispersion forces or these London forces more easily. Molar mass, and I think we're going to see some examples, maybe not today, but later. You know, the larger the thing is you're creating an intermolecular bond with, the more polarizable it is. So I said that actually there would be one more synonym going along with dispersion forces, okay? And this is it. Is this it? No, this isn't it. Van der Waals forces. This is not it. Van der Waals forces, I'm just double checking. It says, according to our textbook, it's everything except for ions. No ions. Okay, so basically, you're looking at hydrogen bonding, ordinary dipole-dipole, dipole-induced dipole, induced dipole, induced dipole. Other textbooks, that's what I thought. Yeah, synonym. Other textbooks would use Van der Waals forces for those induced dipole, induced dipole. But so we call them dispersion forces, London forces, and maybe Van der Waals forces. But don't call them Van der Waals forces in this, because we're using Van der Waals forces for anything except for ions. Chemistry doesn't do a lot of that, but here and there they do. It's like, oh, really? Did you get your stuff together? Okay, so over there on the right we have some simple molecules. Okay, we talked about polarity. There's just two atoms over here. So if you were to go ahead and calculate the dipole moment, this is what it would look like. All right. So the point here is that, notice the one that is nonpolar, F2 is nonpolar, it has no net dipole, okay, moment. And it has no dipole-dipole interactions, makes sense, okay? These others, you can see, since they're polar, you would expect the other three to have, okay, dipole-dipole, keeping those molecules together. This column, though, I think is interesting. This column is what sort of those induced dipole sort of London forces do you have going on, dispersion forces? And the answer is for the thing that's nonpolar, of course, it's 100%. Okay, the thing that's nonpolar, the only thing that's keeping those F2 molecules together is the induced dipole, or the dispersion forces. For the others, though, I just think it's interesting that even though they're polar, to a large degree, they are sticking together because of that induced dipole effect. Okay, so the last two columns speak to how strong are those intermolecular bonds. So the delta H vap, that's the heat of vaporization. That's the latent heat of vaporization. How much energy do you need to zap, in this case, 1 mole of these things, in order to go ahead and go from a liquid to a gas? That's what this column is over here. Okay, and the corresponding temperature that you need to go ahead and, under normal atmospheric pressures, go ahead and have that thing boil. They kind of, actually these two should go together. You would expect, and see if we see it here, you could expect as you increase your heat of vaporization, as you increase the amount of energy you need to zap it with in order for it to go from a liquid to gas, you would expect its normal boiling point temperatures to increase, and actually they do. Okay. So there actually are 4 bars here. I know that with argon and carbon monoxide, you don't see 4 bars. Argon and carbon monoxide, let's see, I don't think carbon monoxide's, well, argon is definitely nonpolar. So the yellow means if you want to get argon molecules to stick together, you have to induce a dipole. That's what the yellow is, induced dipole, induced dipole. Carbon monoxide should have, isn't, I think that's an error, because isn't carbon monoxide, it's polar, right? So where's its blue one? Where's its little blue one? Carbon monoxide, I would have thought would have looked more kind of like, oh, I guess it's there. Oh my gosh. I guess it's there. This is the dispersion. The last bar is simply the total amount of intermolecular bonding. Let's see. HBr? Anybody? Got a little more going on here. More polar, I suppose. The dark blue is the dipole-dipole, and the pink is the dipole-induced dipole. Okay, so if you have the pure HBr molecules sticking together, it still has a lot of these induced dipole, even though the darn thing's polar. HCl. A little more of the dipole and induced dipole. Now, the last two, hydrogen bonding. Okay, so of these, the only one that have the hydrogen bonding are the NH3 and the H2O. But they still have a fair bit of that yellow, which is the induced dipole. They definitely have a significant portion of, this is the dipole, which is not ordinary dipole, it's hydrogen bonding. That's interesting. Okay, so I do have some good hints about this assignment. Well, I think they're helpful. And I'll post them. Okay, so the two questions. This one, of course, there's always more than one part, like we have, 5 compounds. But for each of these 5 compounds, notice that they're in their pure state. They're not in mixtures. We'll talk about mixtures coming up. But you're supposed to describe the importance of dispersion forces, which, as we know, everything has dispersion forces. Okay, dipole, or hydrogen bonding. And so then my hint here is dispersion forces. I put in red under there. That's the nonpolar. That's for sure nonpolar molecules, but we know actually all molecules have dispersion forces. So that'd be all and nonpolar. Dipole, if they're polar, they can have dipole. Hydrogen bonding, a special case of dipole. You need to have the hydrogen bonded to a fluorine, nitrogen, or oxygen. So my hint would be to draw the Lewis structure, determine polarity, and if there's hydrogen bonding. And then just my little thing in red was, like we saw in that last figure, keep in mind that all molecules, all matter is stuck together intermolecular bonds with those dispersion forces. And then the next one looks like this. Oh, I didn't put any brakes in this. Here, let me put some brakes here. Okay. So this all deals with benzene. So the formula for benzene is C6H6. Okay? And we talked about resonance structures in Chem 1, and so actually it's a ring, and I don't know if you can kind of tell the subtle difference between these two, but it alternates single, double, single, double, single, double bond. And notice this one, this goes double, single, double, single, double, single. Okay, so the double bond is in a different place. That's why they're resonance structures. But notice that the best way, I think, to draw this a benzene ring is simply this. Benzene ring, you draw something that looks six-sided as much as possible. You draw a circle in the middle. Actually, this is to kind of represent the fact that the electrons have kind of delocalized, and they're kind of just humming around above and below the plane of that circular, that ring structure. So this is benzene right there, C6H6. And the cool thing about benzene, or one of the many cool things, I guess it's a carcinogen, that's bad, but it's very reactive, which maybe is why it's a carcinogen. So it's really easy to pick up, in fact, you'll learn this in organic chemistry, very easy to kick off one of the hydrogens and substitute something else there. So that's where this problem comes in. So in one case, they substituted a chlorine, in one case, they substituted a bromine, and the third case, they substituted an OH. An OH actually, and I will get to this actually in this unit of material, a little bit of organic chemistry, but the OH is called a hydroxyl group. Okay. The other thing that they give you is they give you the boiling point temperatures. This is all, I'm getting to the problem. So these are the problem. They give you the boiling point temperatures of everything. Pure benzene, well, what if you kick off a hydrogen and put a chlorine? Well, what if you kick off a hydrogen and put a bromine, kick off a hydrogen and put an OH? Notice that as they've given them to you, they've given them to you in increasing boiling point temperatures. And so my last hint here in red is the higher the boiling point temperature must mean that there's stronger intermolecular bonds. So here's the question to you guys. It says, explain. Explain why when you go with just straight old benzene, it looks like this, okay? You substitute a chlorine, a bromine, or a hydroxyl group, an OH group. And here's your hint. First off, before I turn you loose, see, I don't know whether to ask this in the form of a question or to kind of just say what it is. Up here, if we had to say whether benzene is polar or nonpolar, I'm just going to tell you that it is nonpolar. It is nonpolar. You'd be like, well, Mrs. Snipes, I know that I could go ahead, I'll pick green, I know that I could put a partially negative, partially positive. I could do that on all of my carbons and all of my hydrogens. Yeah, you could. I will tell you also the benzene ring lies in a plane. We've talked about plane things like a sheet of paper. So I guess now as I'm standing here, doesn't it make sense that your negativeness probably in the center of your negativeness is in the center of the ring, and the center of your positiveness is also in the center of the ring. So they would annihilate each other. I'm also going to kind of tell you that maybe even Wednesday, when we start to look at identifying polarity, that we're going to see if you see carbon and hydrogen stuck together, I know that there's a difference in those Pauling values, those electronegativity values of the carbon and hydrogen, but it's not much. So actually even kind of any sort of hydrocarbon in general is probably going to be pretty wimpy, non-polar. But bets get off when you put in a chlorine. I'm liking partially negative for that chlorine. Okay, bromine, something special with the hydroxyl group, the OH group. So that's the sort of thing that probably include in your discussion. So again, the benzene ring in and of itself, nonpolar. Okay. All right. And that's it. We'll see you on Wednesday.